Hello everyone. Welcome to the video of my final year project, Travel Time Estimation on Road Networks, Effective Embedding and Traffic Condition Representation Learning. I'm Yang Jingyi, and my FYP supervisor is Professor Cong Gao. Nowadays, people are increasingly reliant on urban mobility apps in their daily lives. For example, people use apps like Google Maps for route planning and Uber and Grab for ride-hailing and carpooling. All those amazing services provided by the urban mobility apps actually depend on algorithms that are able to estimate the travel time of a given trajectory. For example, Google Maps will return to its user the route with the shortest estimated time of arrival, while Grab will use the estimated travel time to assign a passenger the driver that's closest to him or her. Therefore, efficient and accurate algorithms for travel time estimation is really the core of urban mobility apps, and that's exactly what we're going to focus on for this project. Travel time estimation is formally defined as the task of predicting expected travel time or travel time distribution given the trajectory R, which consists of a sequence of road segments Ri. Example is shown on the graph to the right. As the problem of travel time estimation becomes more important, it has attracted the attention from the research community. There are two classes of existing research on travel time estimation. The first class are the traditional statistical models, and the second class are deep learning-based models that emerged in the past few years. Traditional statistic models try to fit the travel time on each road segment into a statistical distribution independently, while deep learning-based method uses deep neural network to extract patterns from historical trajectories to generate an accurate prediction of travel time. Thanks to deep neural networks' representation learning capability, deep learning-based methods have significantly outperformed traditional statistic models. Here's the outline of a typical deep learning-based model for travel time estimation. First, the raw GPS sequence fed into the model are matched into trajectories on the road network through a map matching algorithm. The matched trajectory then goes through the spatial information embedding process, which turns each of the road segments into a vector representation. At the same time, the traffic condition data, which is usually obtained from trajectories within the same time period, is fed into the traffic condition encoder, which turns them into traffic condition representations. Both the row segment representation and the traffic condition representation are then fed into a deep neural network to generate either the expected travel time or travel time distribution. Now, although deep learning-based models have achieved significant performance gain compared to traditional models, they still have ample space for improvement. In this project, we'll be focusing on improvements to both the spatial information embedding module as well as the traffic condition encoder. Let's first look at spatial information embedding. Spatial information embedding is the process of encoding each road segment Ri of the trajectory into the corresponding latent representation ρi. Now, existing methods uses either the multi-layer perceptron or recurrent neural network to do the encoding, which is illustrated in the two diagrams here. Multi-layer perceptron-based encoders can't capture the correlation across row segments because it encodes each row segment independently. Although recurrent neural network solves this problem, recurrent neural network can't be parallelized and is inefficient. Moreover, it suffers from the information bottleneck problem when there is a large number of recurrent modules. In order to address the issues mentioned above, we propose the transformer-based encoder for spatial information embedding. Transformer model has proved successful for a large number of sequence transduction tasks and especially powerful in terms of capture both the long-term and short-term dependencies of elements within a sequence. Here, our transformer-based encoder consists of a stack of encoders. For each encoder, there is a self-attention module as well as a feed-forward network. The road segment representations are first fed into the self-attention module, which effectively captures the correlation across road segments. The output of the self-attention module ZI are then passed into the feed-forward network to generate the latent representation of each road segment. In terms of the self-attention module, we use the multi-head scale dot product attention mechanism as proposed in the original transformer paper. Now let's take a look at the traffic condition representation learning process. Existing methods use convolutional neural network or CNN to encode traffic condition map into traffic condition representation, but this method suffers from incomplete data. A typical traffic condition map is shown below to the left. As you can see from the map, all the black entries represent entries where the data are not collected. Therefore, as a large proportion of data are missing from the map, it limits CN's capability of extracting meaningful feature representations, making the representation learning process ineffective. To address the issue, we propose a learn traffic map completion pipeline. In this pipeline, we use a generative network called the convolutional network to complete the traffic condition map. The completed traffic condition map then went through the masking process, where a mask indicating the road presence is applied to the completed map to eliminate the noise from the generation process. The masked traffic condition map, as well as the road segments, are then fed into the deep neural network to generate travel time. Now, the traffic condition map completion process is supervised by a reconstruction loss, which makes sure that the completed traffic condition map put meaningful data in the missing entries. Apart from improvements to spatial information embedding and traffic condition representation learning, another important area of consideration is whether our model can generate the travel time distribution. As pointed out in previous research, in some cases, it's necessary to generate the travel time distribution in order to solve problems like arrival on time. We are able to integrate the transformer-based encoder and learn traffic map completion pipeline into the deep generative model or deep GTT framework proposed by Li et al. In 2018. The deep generative model learns the travel time distribution by optimizing a variational lower bound. In order to evaluate our model, we use two large-scale public datasets collected from two cities in China, Harbin and Chengdu. The statistics of the two datasets are displayed below. In terms of evaluation metric, we use root mean square error as well as mean average error. The evaluation results of our models as well as the baseline models are displayed here. We use a simple multi-layer perceptron-based model as well as the deep GTT model as a baseline for performance comparison. Note that we evaluate a model with only the transformer encoder, the model with only the learn map completion pipeline, as well as the model that combine the two techniques. As we can see from the results, the model with the two techniques combined achieves the best performance on Harbin dataset, significantly outperforming the original deep GTT model. While on Chengdu dataset, the model with transformer encoder performed best, again significantly outperforming the original deep GTT model. Furthermore, we visualize the root mean square error of travel time estimation by travel distance. As you can see from the two diagrams below, the combined model is able to achieve a more accurate and balanced performance across all travel distance classes. In conclusion, we propose a transformer-based encoder that efficiently embeds a trajectory while capturing the correlation between road segments. We propose a learn traffic condition map completion pipeline to address the incomplete data issue, and the pipeline can be trained with the model end to end. We combine the proposed techniques into a deep generative model to perform accurate travel time distribution estimation. Experiments on large-scale public datasets demonstrate the superiority of our proposed method. That's the end of this video. Thank you for watching.